Welcome to the 16th lecture of Electronic Devices and Circuits 2 course. Our topic in this lecture is oscillators. Oscillators are a very important class of circuits that are widely needed in many different applications, especially communication and also testing. Without oscillator circuits, no testing is possible. So what are the oscillator circuits? Oscillators are circuits that are used to generate signals of different frequencies, signals of different wave shapes, different amplitudes. As you have seen in your lab, that you have a box that we call signal generator, and there are a couple of knobs on the front of that box, and those knobs you use to choose the type of the signal, uh, whether a sinusoidal signal or a square wave or a triangular wave. So you can select the type of signal that you want, and also you can choose the frequency of this signal, the amplitude also you can vary. And that box, we call it signal generator, and the signal generators are a very integral part of our labs. For any experiment you will need, or for most of the experiments you will need the signal generator. You need signals of different frequencies, different wave shapes, amplitudes to test the different circuits that you build in the lab. So what are these signal generators? Inside these signal generators you have basically circuits that generate these signals, and those circuits are called oscillator circuits. So you can understand the importance of the oscillator circuits, how important role they play in electrical and electronic engineering. Without oscillators, no testing of any circuit would be possible, and without oscillator circuits also communication system would be lame. In any type of communication, we need carrier signal to carry these signals over a long distance. For modulation and demodulation, we need signals of different frequencies. And how do we get those signals? So only way to get those signals are using the oscillator circuits. So oscillators are very important. They have a very important role in electrical engineering, and in this our lecture we will learn the basic concepts, the principal operation, how the oscillator circuits work, and we'll see some few example of oscillator circuits. So the diagram here shows the basic structure that is used for the oscillator circuits. It's the same diagram that we have used for the feedback amplifiers, which has the basic amplifier and a feedback network. The feedback network samples this signal, the output signal of the amplifier, generates a feedback signal, and that feedback signal is mixed with the source signal at the input side, and the mixture, the signal Xi, goes into the basic amplifier. So that was the basic structure of the feedback amplifier that we used for our performance improvements of the amplifier circuits, and that same structure is also used for the oscillator circuits, but with one small but very important difference, is that the feedback here in this case is positive instead of negative that we had for the feedback amplifier. So the oscillator circuits basically they work on the principle of positive feedback. So the feedback signal XF here is added with the source signal, and the summation is Xi that goes into the input of the basic amplifier. So this also we can call the signal flow diagram of a positive feedback amplifier. So first we'll see the mathematical analysis of this, and we'll show how this structure can produce a signal, generate a signal without any input signal. So basically the feedback, the oscillator circuit will not have any input signal as is shown here Xs, but this is shown here just to help develop our understanding of the operation of the oscillator circuits, and later we'll remove the source signal. So we start with the input signal Xi, which is the summation of the source signal and the feedback Xs and Xf. The feedback signal here is the output of the feedback network, which is beta X naught. Xf is beta X naught. X naught is the input to the feedback network. Now X naught is the output of the basic amplifier, and which we can express as AXI. Xi is the input of the basic amplifier that gets multiplied by A, and we get the output signal of the basic amplifier AXI. So Xi takes this form, and this we can rearrange, and we can write in the signal Xs in terms of our input signal Xi. So this is how we express finally the Xs in terms of Xi. Now the gain with feedback for this positive feedback structure is the output is X naught and input is Xs. So that is our overall gain, or the gain with feedback. So in this case X naught is AXI and Xs the signal source. We have derived this expression for Xs in terms of Xi. So replacing that here, we get this. Now see that Xi and Xi will cancel out, and then the gain with feedback takes this form, A divided by 1 minus A beta. So that looks very similar to what we have got for the negative feedback amplifier. Only difference here, for that negative feedback amplifier we had a plus here, and now in this case we have a minus. So you see that if A beta is less than 1, and then this whole term in the denominator will be less than 1, and gain AF in that case will be greater than the gain of the basic amplifier. So that makes a big difference in the this positive feedback amplifier with that of the negative feedback amplifier. In the negative feedback amplifier we had 1 plus A beta, and the gain with feedback was always less than the gain of the basic amplifier. But with positive feedback in the this feedback network, this is possible to get a gain higher than the gain of the basic amplifier. So we can have a increased gain, and that makes all the difference for the feedback amplifier of the oscillator. And this was the block diagram of our positive feedback amplifier, and the expression for the gain with feedback that we have derived in our previous slide is given by this. F, which is defined as X naught by Xs, our signal source, and that is equal to A, the gain of the basic amplifier, divided by 1 minus A beta. Now in this case we get an interesting result. If 1 minus A beta is 0, if this numerator, the denominator, the factor here, denominator becomes 0, we get an interesting result. And what is that interesting result? The gain will be infinite. So in AF, when this factor 1 minus A beta is 0, gain with feedback amplifier will be infinite. We have already mentioned that the positive feedback amplifier will give us a gain greater than the gain of the basic amplifier. The smaller is this factor, the higher will be the gain. But you see that when this becomes 0, exactly 0, gain will become infinite. So what is the physical significance, or what is the explanation of this result? This means that even if your input signal Xs is 0, right? Even if your input signal is 0, then even then it's possible to get an output, because that's what it means, that if that is the gain is infinity, means this has to be 0, only then it becomes infinite. You cannot get an infinite output, but it is possible to have a 0 input and have an output without any input, and then the gain will be infinite. So the explanation for this result is that it is possible to get an output with 0 input signal. So whenever you make this factor 0, so you can still have an output with 0 input. So here now we can make the signal X is 0. So first we had this input signal Xs to develop our the mathematical formulations. Now we see that if we make 1 minus A beta 0, then gain we can have an infinite gain, and then it is possible to make it 0 and still have an output X naught. And that is what exactly a oscillator circuit is. Oscillator circuits, they are signal generator circuits. They generate signals, so there cannot be no input. They are the generator, so they are generating signals without any input signal. Of course, you need to provide the power, the DC power, to power up the signal generator circuits. So that power they will mainly use to convert it into an AC power, a signal power. So they are basically converting DC power into AC power, and the frequency of the signal will be determined by your circuit components, and that we are coming how you can fix the frequency of the generated signal for the oscillator circuits. So now in our previous slide we have just learned that if you can make the factor 1 minus A beta 0, so you will have an infinite gain, and then it will be possible to have an output X naught without any input signal Xs. So now here Xs is 0, and 1 minus, provided that 1 minus A beta is 0, so this term is 0, then you can get an output X naught without any input. That means circuit will work as an oscillator circuit. So what is the significance of this statement 1 minus A beta 0? This we can write as this, that A beta is 1. Now what is the significance of A beta? The product A beta is also termed as the loop gain. It is also called the loop gain. Is the product the it will be the gain by which the signal Xi will be multiplied with once it finishes one loop around this feedback network. You see that we have the output signal X naught, and X naught will be AXI. That's our input of the basic amplifier Xi. So output of the basic amplifier is AXI. Now AXI goes into the input of the feedback network, where it gets multiplied by the feedback factor beta. So the output of the feedback network becomes A beta xi. So AXI gets multiplied by A beta. So and then we get XF, the output of the feedback network. The feedback signal is A beta xi. Now this, as you see, that signal has completed one loop around this feedback network. We have xi started here, went through the basic amplifier, then went through the feedback network, and it came back here. Xf, xs is 0, so xi is xf. It goes into the basic amplifier. So that finishes one loop around this feedback network. So the loop gain now we can define, that is the at the output end, right after the end of the loop, xf, and at the beginning of the loop is xi. So loop gain is defined as xf divided by xi. That was the initial value, that is the final value after completing the loop. So loop gain is defined as the xf, the final value, divided by the initial value, and if you do the math you get A beta. So that's why the product A beta is called the loop gain. Every time signal completes one loop around this loop, so it gets multiplied by A beta. Now what if A beta is set to 1? If A beta is set to 1, then xf becomes xi. If A beta is set to 1, xf becomes xi. These two must be same. So that means once it completes the loop, the signal completes one loop, it becomes xi again and goes into the basic amplifier, where it amplified becomes x naught, goes through the feedback network multiplied by beta, and A beta is 1, so it becomes xi again. So every time it goes through the loop, the signal is regenerated. Signal is regenerated every time it goes through the loop. And this is how this is get a sustained signal at the output. It doesn't die out because the output signal is fetched by the feedback network and it is fed into the basic amplifier, and it keeps going on and keeps regenerating the signal xi, and that is multiplied, and you get a sustained output at the output of the basic amplifier, that is x naught. And that is how we get a sustained oscillation. And that is the basic principle how the oscillator circuits work. So you set the product A beta, the loop gain 1, and the signal keeps regenerating as it goes through the loop, and you get a sustained output at the output of the feedback amplifier. And that is the basic working principle of the feedback or oscillator circuits.